In this video, we are going to talk about division of polynomials. Let's begin by talking about dividing a polynomial by a monomial, by just one term. So we're going to look at how to divide any kind of polynomial by a monomial. And in order to do that, we are going to use the rules for exponents. So essentially what we want to do is divide each term of the of the polynomial in the numerator. So in this first example, we have a binomial. In the second example, we'll look at a trinomial. But we're going to divide each term in the numerator by the one term in the denominator. And in order to do that, we are going to use rules for exponents. In particular, the rule for exponents that we use for division, which tells us that if we have two expressions with the same base, like z and z, that we can subtract the exponents in order to divide. For the coefficients, we're going to just treat those as if we were dividing the two numbers, or if they don't divide evenly, we'll think about simplifying like we do with a fraction. All right, so let's take a look at these two examples. So beginning with the first one, where we have a binomial, two terms divided by a monomial. Now what I'm going to do is rewrite each of these two terms divided by that monomial separately, and this is really just to kind of give you a sense of what we're doing. You could maybe skip this step and just divide without having to rewrite it, by just kind of thinking about dividing these two and then dividing these. So for the first expression, I'm dividing the 6 by the 3 to get 2, and for the z's, I'm subtracting the exponent z to the third and z to the second. When we divide, we have z to the first power. For the second term, dividing 9 by 3, I have 3, and the z to the second cancels out. So my quotient here is also a binomial, 2z plus 3. In the second example, we have a trinomial. So once again, I'm going to rewrite each of the terms that are in the numerator and divide by the denominator. Once again, you can skip this step if you're comfortable doing that visually. When I do that, I will see that my result will also be 3 terms because I have now 3 divisions that I need to perform. Right, so for the first term, the 2's cancel out, the x squareds cancel out, because when we divide something by itself, we get 1. So I'm just left with y to the first there when I subtract the exponents. The second example, I have 9 divided by 2. I cannot divide it, so I'll just leave that in fraction form. It is also simplified. Let me just extend my fraction bar here. So let me just pause for a second there. Okay, hold on. So for the x's, when I subtract, x to the first is a smaller exponent on top. So when I subtract, I actually get a negative exponent. So I really used 2 exponent rules here. So I divided by subtracting the exponents for the x, 1 minus 2, which gave me x to the negative first. But instead of writing x to the negative first in the numerator, I put x to the positive first in the denominator. So it's using 2 rules there, the division rule, the quotient rule, or, and the negative exponent rule. As a shortcut, you can just subtract your exponents bigger minus smaller, and then wherever the exponent is larger, that's where you write your expression. And likewise for the y's, we had y to the third and y squared. When we subtract the exponents, we have 1, but since the exponent was higher in the numerator, the y to the first stays in the numerator. All right, we're going to see that in the last term as well. So for the last term, we're dividing 16 by 2. 16 divided by 2 is 8. The x squareds are going to cancel each other out because they are the same. And then for the y's, when we subtract the exponents, this is y to the first on top, y to the second on bottom. So 2 minus 1 is 1, but we're going to write the y where the exponent was larger, which was in the denominator. So here we have 3 terms, y minus 9 over 2 times yx. We could maybe write that a little cleaner. So y minus 9y over 2x plus 8 over y. Notice we had 3 terms in the numerator. We have 3 terms here. But it also is important to note that in this case, because we have variables in denominators, the quotient is not a polynomial, which is interesting because for the other operations with polynomials, addition, subtraction, and multiplication, when we do the operation, the result is also a polynomial. The operations of addition, subtraction, multiplication are closed in the group of polynomials. But in this case, the group of polynomials is not closed, or the operation is not closed under that group. Okay, so we are going to also look at long division in this video. So let me just remind you about dividing two whole numbers here. So when we're dividing long division of polynomials, the setup is going to look pretty much like we see here. So when we are dividing whole numbers, sometimes we go kind of piece by piece. So if we were dividing 875 by 25 in this case, we wouldn't necessarily think about 25 into 875. We would kind of go digit by digit until we get a number that we can actually divide. So in this case, we would be dividing 25 into 87, putting that value on top. Then it's a process of multiplying back. So 25 goes into 87 three times. 3 times 25 is 75. We subtract and bring down the next digit. So division is an algorithm, which just means that we perform a set of steps over and over and over again. So the set of steps here are divide, multiply, subtract. So when we bring down that 5 here, we are then dividing again 25 into 125, which goes 5 times, multiply back, we get 125, subtract, and here we have 0. So the value that you have left over at the bottom after you've used all of the digits is your remainder. So a remainder could be 0, or it could be something else if our number doesn't go in evenly. So we're going to see that with polynomials as well. All right, so let's go to our examples. Actually, let me show you the examples that we had first before we continue. Sorry about going back and forth here. So we're going to look at these 3 examples in the next step. So we have 3 examples. These are all trinomials divided by binomials, but the process is the same no matter what kind of polynomial you're dividing by a binomial or something higher. All right, so let's take a look at the first example. Okay, so here I am rewriting so that the denominator goes on the outside of the division sign and the numerator goes on the inside. All right, so we're going to begin this process of division, but we're going to divide one term of the trinomial of the numerator by one term of the divisor. So off to the side, I'm going to write a list of what you should be thinking about when you're dividing. So what I write kind of off to the side here is just kind of optional. It's what you're thinking about. But that's really the division that's being done. We're dividing everything by the first term of our divisor, which in this case is x. All right, so I'm thinking about dividing x squared by x. So these are my steps off to the side here. This is what we're thinking about. X squared divided by x, the first term of the dividend by the first term of the divisor. Using your rules for exponents, that is x, and that goes in the numerator. Now, I like to line up the, not the numerator, in the quotient. I like to line the like terms up with the like terms in the dividend just to help me to kind of see how many terms I have left to divide until I get down to my quotient and my remainder. So this is x to the first, and I'm lining it up over my x to the first term. Now we went through the process of division, so we'll then go back and multiply x times x, but then also x times 3. When we do that, we are going to write the terms underneath the like terms in the dividend. So when I multiply back, I have x squared plus 3x. Now I need to subtract that. Notice I'm using parentheses here. I'm subtracting those two terms. I always write it that way first, and then I change to addition and negate the signs. Make sure you negate both signs. So the first two terms should always cancel out here, and then make sure that you are adding appropriately. So that gives us negative 7x. We're going to bring down our next term, negative 21, and repeat the process. Now I'm dividing once again, but I'm dividing negative 7x by x. So that's what I'm thinking about, and I'm just writing that off to the side here. When I divide those two terms, I'm left with negative 7, and that goes in my quotient up top. Again, I'm lining that constant up with the constant in the dividend. Now I'll multiply back. Negative 7 times x, negative 7x. Negative 7 times 3 is negative 21, and subtract those two terms. I'm going to change my subtraction to addition of the opposite. And in this case, both terms cancel out, so my remainder is 0. So it leaves me with a quotient of x minus 7 and a remainder of 0. Okay, let's move on. Oh, if we wanted to check, by the way, I'm going to leave the check to you, but if you wanted to check, you could check by multiplying. The quotient times the divisor plus the remainder should give you the original polynomial back, or the numerator of that expression. So you can check that and make sure that both sides of that statement are equal. All right, so let's move on to the next example, number 2. We have another trinomial divided by a binomial, just rewriting. The binomial goes outside. Well, because it's the divisor in the denominator, that's why it goes outside, not because it's a binomial, and the numerator goes on the inside. So once again, we're going through that algorithm of divide, multiply, subtract. So I'm dividing 4x squared by 4x, and that gives me x. Multiply that back, I have 4x squared plus 7x. Go ahead and subtract. Which means I'm adding the opposite. And when I add the opposites there, I end up with negative 24x. Bring down the next term, negative 33. Now I repeat the process, dividing negative 24x by 4x. And that gives me negative 6. The x's cancel. Negative 6 goes in the quotient. Negative 6 times negative 4, or excuse me, times 4x is negative 24x. Negative 6 times 7 is negative 42. I will subtract those two terms. And I'll subtract by adding the opposite. So see, in this case, the first terms cancel out, and they always should, but the next two do not, which means I now have a remainder. So my remainder in this case is 9. And of course, you can check that in the same way that we had checked the others, but let's go on to the next example. Okay, in the last example, I've begun to set it up, but I want you to notice one thing here. In the numerator, I have a term missing. The a squared term is missing, but I need to have a term as a placeholder here. Otherwise, I won't be able to combine like terms. So I put a 0 a squared as a placeholder. So now I could go ahead and continue the process of division, then multiply, then subtract. In the first case, I'm dividing a to the third by a, and that gives me a squared, and I'm putting that over my a squared term. So now when I multiply back a squared times a, that gives me a to the third, and a squared times 8 gives me 8a squared. So I needed that 0a squared in order to line that up. I'm going to go ahead and subtract those terms, which means add the opposite, and that gives me a negative 8a squared. I'm going to continue and bring down the next term and repeat that process. All right, just to speed this up a little bit. So what I had done was divided the negative 8a squared by a to get negative 8a and multiply that back. So just take a moment if you need to pause this and just check what you see here. Now we'll go ahead and subtract that. So adding the opposite. Okay, so then I went ahead and took the next step as well. So after you add, you have 15a at the bottom. Divide by a, you have 15. That 15 goes up top, multiply back. So again, take a moment, pause this, check these steps. And then when you add the opposites, you have a remainder of 0. So in this case, the quotient is a squared minus 8a plus 15, and the remainder is 0. I hope you enjoyed this video. Thanks for watching.